Yes, thank you. So I would like to thank the organizers for inviting me and for giving me the opportunity to talk. It's a pleasure to be here again. So this will be joint work with Cornelia Drutu, Panos Papasoglu, and Stephan Stadler. So we are interested in isoperimetric inequalities for Lipschitz two spheres in spaces of non-positive curvature, like Hadamard manifolds or cat-zero spaces. So a very simple situation. We are just looking at the Lipschitz map from the standard S2 into our space, and we would like to extend it to a Lipschitz map on the 3-ball. Okay? So that one has a good estimate on the volume of the map in terms of the area of the boundary. So a very simple situation, but surprisingly, it's still not completely solved. But for the history, let me start with one dimension less. So I'll start with the simplest possible situation in R2, closed curve bounds, well, the area bounded by a closed curve is at most 1 over 4 pi times the length squared, right? Very classical fact. And now, if you go to non-positive curvature, André Weil already in 1926, he observed that the same holds in two-dimensional Hadamard manifolds. Okay. Same in 2D Hadamard manifolds. So now we want to go to higher codimension. So we are still looking at the Lipschitz curve, but then in higher codimension, the filling is no longer canonically given. So we need to produce the filling, and then an isoperimetric inequality becomes an existence result, right? So given a curve, there exists a filling so that you have a certain inequality. And in this context, there is Reshetniak's result. It's called Reshetniak's majorization theorem from 1968. So this says that, well, here X is now a cat-zero space, so a metric space, complete metric space of non-positive curvature in the global Alexandrov comparison sense. I guess for this audience here, I don't need to explain what cat-zero spaces are. Right? Cat-zero space, and you look at a curve, say parameterized by arc length into your space. And then he says that this will factor through a convex curve in R2. So here you have R2, and you find a convex curve. But there is one degenerate case. It could be just a line segment, which is, and then you go along the boundary of this line segment. But yeah, so there's a convex curve, and this will factor. So here you still have an arc length parameterization of this curve, and here, again, length-preserving map to this curve in space. And in fact, this map here also extends to a one Lipschitz map on the interior of that curve. So you get a one Lipschitz map from this convex set into your space, and this produces a filling, right? And now, of course, so-called is F, then the area of F, because this is one Lipschitz, is at most the area of C, this convex set. And by what we have here, this is at most 1 over 4 pi times the length squared. So in cat-zero spaces, you get from Reshetniak's result, you get the optimal isoperimetric inequality, right? Yeah, maybe I should say very briefly something about the area. So if you are in a Hadamard manifolds, then manifold, and here you have a Lipschitz map, then you have a Rademacher's theorem. So almost everywhere the map is differentiable, then you can still define the Jacobian. But the same works for metric spaces. So there is a metric notion of metric differentiability, a metric notion of the Jacobian, so the area distortion factor. And then you can still talk about the area of a map. That's a slightly technical point. So the next result I would like to mention is Gromov, so he observed in his paper on hyperbolic groups that a geodesic metric space is hyperbolic, so delta hyperbolic. And again, I guess everybody knows what geodesic hyperbolic space is, if and only if X satisfies a linear isoperimetric inequality. And this is also equivalent to X satisfying a subquadratic. So, of course, well, that's not a precise statement here, because a geodesic delta hyperbolic space might be something rough, like a Cayley graph, and then there is no area. But there are various ways to make this precise. So, for example, if you have a finitely presented group, then there's a combinatorial way to talk about the area. So, if you have a word representing the identity, then you look at a number of conjugates of relators to count the area, and so on. Or you can add the assumption that X is like a polyhedral complex or something, a nicer space where you do have a notion of area. So here you see this gap, right? Well, actually, back from here to here. Okay, so there is the gap. So, and I'll give a precise statement in a minute. So as soon as you have a subquadratic isoperimetric inequality, you already have a linear one. So, and there is nothing in between. It's automatic, an automatic improvement. So, well, many people gave detailed proof of these implications, including some people here in the room. And a particularly nice proof of this fact is due to Bowditch. So he looks at a geodesic metric space with only two simple axioms, for the area. So you look at set of all closed rectifiable curves, gamma, and then you suppose that you have an area function. So you should think of this as a, well, filling function, right? Area of some minimal surface or something like that. And he has two simple axioms. So the first of these is that if you take one of these curves and you subdivide it by a geodesic, then you get two closed curves. And then the condition is that the area is at most A1 plus A2, if these are the corresponding areas. That's the first axiom. And the second axiom is that if you have a closed curve and you subdivide it into four segments, into four parts, and then you measure the distances of opposite segments, then the area should be greater or equal to d1 times d2. Okay? So this is motivated by the Bezikovich inequality, which holds in every reasonable context. And then you define the profile, P of L, as the sup of area of gamma, where the length of gamma is at most L. And then he proves that if PL is big O of, little o subquadratic, little o of L squared, then you get big O of L. Okay. So subquadratic implies linear. And the proof is quite short, so just two simple axioms for the area, and then you have this conclusion. Now there is a sharp version of this due to Wenger. So this says that, again, if X is a geodesic metric space, now you suppose that there exists a constant which is just a little below the optimal constant. So suppose there exists C strictly less than 1 over 4 pi, such that every sufficiently long, so there's another constant involved. Lipschitz curve, closed curve, extends to a Lipschitz disk with area of f less than c times length of gamma squared. So you assume this isoperimetric inequality just with a constant strictly less than the optimal one, then in fact the space is Gromov hyperbolic. Okay. So that's Wenger's result. And another result I would like to mention here is the following. So this is due to Lipschitz and Wenger from 18. And there's a second paper by Stadler and Wenger. So they had slightly different assumptions. I think in the first paper, the space was still assumed to be proper, if I'm not mistaken. So this says that if you have just a complete metric space, complete geodesic metric space, and again you have, well, now you simply assume that you have the optimal isoperimetric inequality. So again with C equal to 1 over 4 pi. Then in fact the space is cat zero. So the isoperimetric inequality, the optimal isoperimetric inequality characterizes cat zero spaces. And the reverse implication is due by Reshetniak, right? So that's all I wanted to say about dimension 2. So now let's go up to the dimension we are interested in. Yes?
So for the result saying that if the constant is less than 1 over 4 pi, then x is Gromov hyperbolic. So does this mean that actually the isoperimetric inequality is now linear?
Yes.
Okay.
Yeah, that's true. So again, you have this gap, right? So all you need is something slightly better than the Euclidean isoperimetric inequality, and then you get, then the space is Gromov hyperbolic and has a linear isoperimetric inequality. Yes. So now let's go to R3. Let's again start with the classical case. So we look at some spaces, might have some topology. Say the compact domain with a smooth boundary. So then the volume of D is bounded by, now the optimal constant is 1 over 6 times square root pi. Okay. Now the exponent is 3/2. Right? So that's the optimal isoperimetric inequality. Of course, I should have said equality holds for the disk, right? That's what makes it optimal. Here, volume equality holds for the ball. So again, if you go to non-positive curvature to Hadamard manifolds, an old result of Bruce Kleiner is that the same holds in 3D Hadamard manifolds. Now, actually, the only other case which is known is the 4D case, which is due to Croak. So then again, if you take in R4, the optimal isoperimetric inequality will also generalize to 4-dimensional Hadamard manifolds. But I'm interested in the 3-dimensional case. So again, now if we go to higher codimension, so we are looking at the 2-dimensional cycle in a possibly high-dimensional Hadamard manifold, well, then there is this result due to Schulze from 2020. So now X is any Hadamard manifold. Now we are looking at so possibly high dimension, and now we are looking at a 2-cycle. So here I really mean an integral current. But if you don't know about currents, just think of some kind of cycle like a Lipschitz cycle, singular cycle. With Lipschitz simplices, that would be fine. That's an example of an integral current. So then there exists a filling, so a 3-dimensional chain V with boundary equal to S. And again, you get the optimal isoperimetric inequality. So now it's the mass of V, which is less than or equal to 1 over 6 times square root pi times the mass of S to the 3/2. Okay? So here mass, well, integral currents, they might have some integer multiplicity, like Lipschitz cycles with Z coefficients, right? And mass is area counting multiplicity. So that's amazing, right? To get the optimal result in Hadamard manifolds of any dimension. And in fact, the proof uses mean curvature flow. So apart from this, maybe as a last result, the optimal inequalities are known in Euclidean space by an old result of, well, of Almgren from 1986. Optimal isoperimetric inequality in Rn for k cycles. Okay? So in this setting here, setting of integral currents, yeah, and that's still an open problem whether this holds in general for Hadamard manifolds. So that's all about the history. Now let me state our result. Yeah, good. So from now on, I will assume that X is a proper cat-zero space and F is a Lipschitz map from S2 into X. And then we define the filling volume of F as the inf of vol F. Yeah, maybe capital F. So if F is a Lipschitz map from the three-ball extending F, right? So that's the filling volume. So here is our statement. The following are equivalent. First, some space. First, there exists a constant strictly less than the optimal constant in the 3D case, so 6 times square root pi, such that every F Lipschitz of large area has fill volume volume, filling volume at most C times area of F to the 3/2. So again, we assume that we have something slightly better than the optimal Euclidean isoperimetric inequality. Then this will imply that, well, we would expect a linear isoperimetric inequality. That's not quite what we get, but we get it for exponents arbitrarily close to 1. Okay? So for all delta n0 1/2, there exists C depending on delta such that every F, again, from the two-sphere has filling volume at most C times AF. Now, with this exponent 1 plus delta. Okay. And there is a last assertion. X has asymptotic rank at most 2. Okay. So I'll explain this in a minute. So here we have the gap, right? And yeah, it's tempting to just state it as a gap theorem like this. But then without this information here, it's maybe not so clear to what kind of examples this would apply to. Okay, so, and in fact, the proof proceeds like this. So we proved that 1 implies 3, and then we go back from 3 to 2. So that's the proof, how the proof proceeds. Okay. So asymptotic rank, well, if you know about asymptotic cones, then this condition is equivalent to saying that no asymptotic cone contains 3 flat, which is isometrically embedded Euclidean space, dimension 3. And if the space is just a simpler characterization, if the space is co-compact, so X co-compact, then the space itself contains no 3 flat. So in particular, the result would apply, for example, if you take a Hadamard manifold, or say a manifold of compact manifold of non-positive curvature, and the universal cover contains no copy of no isometric copy of R3, then the result would apply, and you get this gap. Okay. So of course there is this conjecture which you can find in Gromov's. Well, this notion here, asymptotic rank, this stems from Gromov's discussion of a number of asymptotic invariants for infinite groups in his famous article, and this has been studied by a number of people and refined, and so this conjecture is also in that text, but maybe a bit implicit. So encoded in these notions of asymptotic rank. Of course, we expect that asymptotic rank at most k would imply a linear isoperimetric inequality. For k cycles. And so far, this is known for, well, certainly symmetric spaces of non-compact type and rank k. So these are the prime examples of such spaces. So there is a sketch in Gromov's book. And apart from that, well, it's also known for homogeneous Hadamard manifolds. So this is due to, there's a paper by Hjalti Isleifsson, a student of mine. All right. So that's about the statement. Now let me tell tell you a little bit about the ingredients before we go to some ideas of the proof. So there is this second result, which, yes? Oh, a question.
If in the co-compact case, you said the delta would be 0?
No, we cannot do this. So we don't know. Still not. That's conceivable. So yeah. So question, is it actually linear or is it just close to linear, right? We don't know. So maybe the truth is really that if the space is not co-compact, then maybe 1 plus delta is the best thing. And if it's co-compact, then we would expect linear. That might be the truth. But we no. So here, this result, this should be somewhere. This should be known. So here, x is not necessarily proper. So that's simply the Euclidean isoperimetric inequality, but now for ball fillings of spheres. Right? So, I mean, there is the non-optimal isoperimetric inequality holds in great generality. So this was in Gromov's paper on filling Riemannian manifolds. There was an earlier paper by Michael and Simon. And then there is Stefan Wenger's shorter proof of this fact which holds for all Banach spaces, for all spaces satisfying some kind of weak non-positive curvature condition. But that's for cycles, integral cycles. Right? And here is the corresponding statement in this context for Lipschitz spheres. So there exists C bar so that every, again, f from S2 has filling volume at most C bar times AF. Now let me write the exponent as 1 plus 1/2 because it's 1 plus delta up there, and here it's 1 plus 1/2. So that's just the Euclidean isoperimetric inequality, and here C is a non-optimal constant. Okay? So we prove this, and the proof follows Wenger's strategy. Okay? So, and the fact that we start with a two-sphere allows us to control the topology of the filling. So, but there are some technicalities in the proof. So proof follows Wenger's strategy. So the point of this is that this implies, well, that's a trivial observation. So of course this implies the delta isoperimetric inequality for small areas. So this implies 2 for, well, if the area, so we have different exponents, right? But if 1/2 minus delta, if this area here is at most C divided by C bar, then you get the delta isoperimetric inequality. So we can use this as a basis for an argument by induction on scales. Right? So for sufficiently small areas, the delta isoperimetric inequality holds, and we can hope to proceed from there. And that's kind of what we do. Well, not quite, but you can think of this as the strategy of the proof. Another ingredient is solution of Plato's problem. So every Lipschitz circle, right? So in the proof of this result, we will have to decompose the sphere into smaller parts and then produce some new smaller cycles. And in order to do this, we'll use minimal surfaces. So every Lipschitz circle extends to Lipschitz map from the disk to disk with minimal area. So, well, this technique of minimal surfaces in metric spaces, minimal disks, was developed by, in the past almost 10 years. So Littler, Wenger are involved, Stadler, Kreuz, from say 17 to 22, series of papers. So, well, these minimal disks, they are constructed in, well, as energy minimizers in a certain Sobolev space. So at first they are in W12, in some metric Sobolev space, and then they only have some Hölder regularity. But then there are some tricks to reparameterize the disks and to reparameterize them by a Lipschitz map. So you indeed find a Lipschitz map from the disk which minimizes the area. All right, and now what we do, well, we define minimal triangles. So this is simply a minimal disk filling a geodesic triangle. You can do this. So whenever you have a geodesic triangle, you can fill in a minimal disk. Okay? And now we look at minimal tetrahedra. So that's a Lipschitz two-sphere formed by 4 minimal triangles. So we pick 4 points in our metric space, then they span 4 geodesic triangles. And then we fill in a minimal triangle in each of them, right? Somehow like that. And again, this can be parameterized on the two-sphere. That's what we mean by a minimal tetrahedron. Okay. Now we have the following result for minimal tetrahedra. So in this case, for minimal tetrahedra, we do get a linear isoperimetric inequality. So if now the asymptotic rank, and that's how we proceed, right? So we go through the asymptotic rank is at most 2, then there exists a constant so that every minimal tetrahedron F has filling volume at most is constant times the area of F. So for minimal tetrahedra, we do get a linear isoperimetric inequality. Right. So now a few words about the proofs. Yeah, let's start with the proof of this result here. So a crucial fact, a key fact here is that minimal triangles, which are the sides of minimal tetrahedron, minimal triangles satisfy a density bound. So let me just denote it by T in X. Okay. They satisfy area. So take any ball in your space, any center, any radius, and look at the intersection with T, then the area will be bounded by 3 pi half times a radius squared. Or if you divide by r squared, then here you see the density quotient, okay? And this is uniformly bounded. And that's the key fact which makes everything work. So if we had this result for higher dimensional minimal simplices, in this context, it's restricted to spheres and balls. But we have another result now for, I'll come to that later, for cycles. So the way we prove this is the following. So here is the minimal triangle, right? In the space, in our cat zero space, then we attach a geodesic ray to each vertex, infinite rays, but they stick out of the space, right? So they are glued to the space, added to the space. Then here we have a geodesic line. So with this extension, the space is still a cat zero space. And then we have a geodesic line in the space, well, actually 3 geodesic lines. And to each of them, we glue a Euclidean half plane. Okay, so again, here you glue a Euclidean half plane, the same here, the same here. And again, these half planes, they stick out of the space, right? So you extend your metric space. And then you can prove that you get a plane, yeah, topological plane, and this turns out to be a minimal plane. So it's still area minimizing. So here it's kind of clear because we have a minimal triangle, and outside there is no room to move, right? So it's a minimal 2-plane. And then you can use the monotonicity of the area density. So there is a monotonicity formula for minimizing, for minimal planes. So I can take any point, and then the density quotient is monotone, so non-decreasing. But asymptotically, you know what you have, right? So seen from far away, this looks like 3 half planes, Euclidean half planes. So the asymptotic density quotient will simply be this number here, 3 pi half. And so by monotonicity, it also knows scales and locations. So that's a trick which is in one of Stephan Stadler's paper on minimal surfaces. So the upshot of this is, so this holds for all x, for all r. The upshot of this is that now you can look at the cycle S. So that's our minimal tetrahedron, right? So this will give a cycle, 2 cycle with a bounded density. At all scales. And this puts us in the position to refer to results which we had in the paper with Bruce Kleiner and myself, and in the follow-up paper with a student, Tommaso Goldhirsch. So in that paper, we proved a linear isoperimetric inequality for cycles satisfying this kind of density bound. But then the constant in the linear isoperimetric inequality will depend on the density bound. Okay. So by some results in these papers, there exists V, a filling of this cycle, and it has a linear mass bound, but that's, in fact, we are not even going to use this. So there's a linear mass bound, but then it also has, the cycle also has bounded filling radius. So this filling V lies within uniformly bounded distance of the cycle. And that's what we're going to use. So the point here is that this produces a chain, right, filling the cycle, but we want to find the Lipschitz ball. So we are not yet there. Then what, I need to check my time. Okay. But then what you do is, so this is in a bounded neighborhood. Of S. Now, from these density bounds, one can also prove that the cycle has a Nagata dimension 2. So there is this metric notion of dimension. And once you have Nagata dimension 2, you can prove that everything embeds in a two-dimensional simplicial complex. Now, in that complex, we can, maybe I write this down. So there exist Lipschitz maps. So call this neighborhood K. Then we can, well, the cycle has finite Nagata dimension, but if you are on a sufficiently large scale, you can also include this bounded neighborhood, and then you can map the entire neighborhood into your two-dimensional simplicial complex. So there exist Lipschitz maps from K to sigma, 2D simplicial complex, and then back to X. And the composition of the two maps has bounded displacement. Okay? So you can map into the complex and then back. Now, in this complex here, you can, so there is a trick which goes back to Brian White. So what you do is you cone off the one skeleton of this complex, and you get a simply connected complex, and then you use the fact that the Hurewicz homomorphism from pi2 to h2 is an isomorphism for simply connected spaces. And this allows you to produce a Lipschitz filling, a ball filling. So using the fact that homology of integral currents and Lipschitz chains are isomorphic in this context here. And then you can map this back to X. So maybe I'll abbreviate and just write use Hurewicz. So this goes, it's a trick due to Brian White from the 1960s. Right. So that's how we prove this result. Okay. So now for the proof of the main result, maybe I'll be very brief on 1 implies 3, because that's more or less by now a standard argument. So that's an indirect proof. And so the most interesting part is 3 implies 2. So I would like to explain this in more detail. Well, in fact, this implication 1 implies 3, this works in all dimensions. So this does not depend on 2 dimension. So whenever you have a constant which is strictly less than the optimal constant in the Euclidean isoperimetric inequality in Rk, say, or Rk plus 1, then you get asymptotic rank at most k. Yeah. Yeah, maybe just very briefly. So proof of 1 implies 3. Indirect. So then this gives certain maps, say roughly isometric maps from a unit ball into a rescaled copy of your space, and sequence of such maps with better and better constants. So, and then you can improve these maps to honest Lipschitz maps. And so we have an integral current, and you can solve the Plato problem for the boundary of that integral current. And then you have the mass bounds, the density bounds for the minimizing currents. And this allows to prove that these sets, a support set of these minimal fillings, are equicompact. Then you can use Gromov's embedding theorem and map everything into a single compact metric space and make everything converge. And then you get a configuration in an asymptotic cone. So if the asymptotic rank is bigger than 2, then in some asymptotic cone, you get a contradiction. So what you produce a configuration like this. So you have a three-dimensional ball, so isometric copy of a three-dimensional ball in some asymptotic cone, and you have this limit of the minimizers, so solving the Plateau problem, so same boundary, you get some filling V, and by the assumption this will have mass strictly less than the ball, okay? And now, because we are in an asymptotic cone, so that's still a cat-zero space, this is a convex set, so there is a one Lipschitz projection onto the ball, and this gives a contradiction. And so if you map this filling to the ball, then you have something with smaller mass than the ball, but it has to be the same as the ball, right? There's only one filling here of this ball as a current. So this gives a contradiction. So that's how we prove this implication. Okay, now maybe the most interesting part, 3 implies 2. Yeah, so there are 3 steps, or a couple of steps. So I'll describe it as an induction on scales. That's not exactly what we do. For technical reasons, we have to do it a bit differently, but let me explain it in this way because this also served as a guideline for us, or as an outline of the proof. Of course, the idea is to use this linear isoperimetric inequality for the minimal tetrahedra. And so in order to bring this into play, we need to approximate our cycle by a piecewise minimal cycle. Okay? So the idea is to triangulate the two-sphere, and we have to choose a scale which is quite large, relatively large, so that it works. So the scale is the area of the two-sphere, and then we take the exponent 1 minus delta half. So without the delta, this is just the scale invariant natural scale, right? So that's the kind of the top scale, area f, square root of area f. And we just take a slightly smaller scale. Okay. So by this I mean, well, triangulate by, say, rectifiable curves, okay, in S2. So relative to f, we need the following properties. So the number of simplices is bounded by, yeah, some constant times area of f divided by s squared. So you can think of this as, well, each of the simplices should eat up area approximately s squared. And then that's how many simplices you get. And so scale S, so this means that the f length of edges is at most s, approximately. And then we also need a diameter bound of the vertex set. So we only need to bound the vertex set. Okay, so there might still be some thin parts sticking out of the surface, but we can control the vertex set diameter at most AF divided by S. So notice this is n times S. So we get this in a cheap way, right? So we simply estimate the total length of the entire net on our two-sphere. Just number of simplices times the scale of the simplices. So very rough estimate, but it works. So that's the first thing. And now we deform each simplex into a minimal simplex. So, well, triangles, right, into minimal triangles. So this gives a picture like this. So here is one of these, So this would be one of these minimal triangles triangles of the triangulation, and then we simply keep the vertices and we put the geodesics here, right? And we replace it by this minimal triangle, and then there are also these parts here which we fill, and this produces small two spheres, right? So here we have this part on the surface, and then the minimal triangle, and altogether we get a small two sphere. So this gives small two spheres. But again, so they are at the smaller scale, right? And so we can fill them by induction on scales. So we assume that we already have the delta isoperimetric inequality for these smaller two spheres. And they have area at most, again, s squared. Now fill each of them by the delta isoperimetric inequality. Induction on scales. So this gives a homotopy from F to some new map F bar, which is now piecewise minimizing. It's composed of minimal triangles. So the volume of this homotopy is at most, well, what do we get? N times. So here we have area s squared. We fill them by the delta isoperimetric inequality, so that we get s squared to the 1 plus delta, right? And there are that many small spheres, that many simplices. Now you see that n times s squared is just the area of F. And then there is still this term s to the 2 delta. And if you plug in the scale, then you get area F to the 1 plus delta minus delta squared. So for this part, we actually get something slightly better than what we need. Right? All right, and now, I'll need this picture here. So what we do is we now, of course, cone off. So we pick a fixed vertex, and then we take geodesics to all vertices. Let me draw it here. Like that. So this produces new geodesic triangles. Then we fill in minimal triangles. Then we get a minimal tetrahedron for each of them, right? So now here we have D, this diameter D, and here we have the scale S. And so the area of this minimal tetrahedron is approximately D times S. Okay, there's a smaller term here, S squared. So it's approximately D times S. So that's the last part. So cone of the vertex set from some fixed vertex fill in minimal triangles. So this gives minimal tetrahedra with area, again, at most T times S. Which is AF. So they have approximately the same area as the entire cycle. Right? Now we fill each of them by this linear isoperimetric inequality, 3. So this gives a filling capital F from B3 of F bar, so this piecewise minimal map F bar, and the volume of F is at most n times AF, right, where AF comes from here, because we have the linear isoperimetric inequality for this filling, so n times area F, which is AF squared divided by S squared, which is what we want. So this is AF to the 1 plus delta. So now you combine the two things. So you combine the homotopy from the given F to the piecewise minimal F, and then you add this Lipschitz 3-ball, and you add up the fillings, and this gives the result. So that's how, yeah, that's not exactly what we do, as I said. So there is, yeah, what we actually do is, the proof is indirect. So we suppose that the delta isoperimetric inequality fails for some large multiplicative constant and for some fixed delta. And then we take an almost minimal counterexample, okay? And we use the properties of this almost minimal counterexample to decompose the sphere, to do this triangulation, okay? So, because if you work with this almost minimal counterexample, then this implies some intrinsic isoperimetric property of the two-sphere, which we can use to decompose the two-sphere. And that's how it's actually done. But still, that's kind of a reasonable outline. So that's for cycles. And now in the last couple of weeks, we got, sorry, that's for two spheres. The last couple of weeks, we got the same result for cycles. So for two cycles and fillings by integral currents. But this still requires an extra condition. So we need to assume that the space has finite Nagata dimension. So here, the fact that we start from a sphere allows us to control the topology and to produce a decomposition. And if we start with a general cycle, then it's much harder. But if you assume that the space has finite Nagata dimension, then there are good coverings, and then there are still some tricks to map into simplicial complexes and use this to produce a suitable decomposition of the cycle. And then we can prove the same result for cycles. But it's still restricted to asymptotic rank 2. So if we had this density bound for the minimal tetrahedra, that's the only restriction. So if we could generalize this to high dimension, then we would get the result in all dimensions for cycles. Well, for high dimension cycles, still in, no, it's correct what I said. Yeah. Right. So I should stop here. Thanks.